This conference will now be recorded.
Our TikTok session of today is entitled Recent Development in 5G EMF Policies, Guideline, Radiation Measurement and Monitoring. And we have here our speaker of the day, Encik Anwar Faiz Osman. So Encik Anwar, you may take over the session from me, and perhaps you can start by introducing yourself to all of MCMC staffers. Thank you.
Thank you. Aisha, right?
Yes.
Yes. Okay. Good afternoon, everyone. My name is Anwar from Radio and Shorts Malaysia. I'm a regional application engineer working on mobile network testing. I'm also the vice chair of the MT and Future Network Working Group, the MTFSB. This working group is responsible to produce the technical code for the 5G base specification and also the EMF exposure from the base station. Right. So without further ado, let me start with the presentation. So I'm targeting about 50 minutes of presentation and 10 minutes for question and answer. So the title of this presentation is the recent development in 5G EMF policies, guideline, radiation measurement and monitoring. This presentation is a follow-up from the previous presentation that I've given in the talk as well last year. So we have got some updates for the 5G EMF measurement and methodology. So the agenda for today, I have 4 agenda. First is we will discuss on the overview of 5G antenna and power radiation technology and why is it important when we want to consider for the EMF measurement. Second, we will go into case study on recent development of 5G EMF exposure policies, guidelines and standards at various countries, Switzerland and the UK in particular. The third agenda will be the differences of 5G EMF radiation measurement as compared to legacy 2G, 3G and 4G mobile technologies. The last agenda, I will present on the case study of 5G EMF measurement from actual site in Malaysia, one in KL and one in Langkawi. And we will end up with the summary. So let's go on the first agenda, which is the overview of the 5G antenna and power radiation. So what is 5G? So we talk about the previous generation of mobile communication, right? The first generation is more on the analog communication, right? Where you see this old brick type of mobile handphone, mostly it's being used for voice communication, and this is about in the 80s. So when we come to the 90s, we start the second generation mobile communication. We start to have not just the voice, but also the digital communication, where we have the SMS, right? And then about 10 years after the second generation, we have the third generation of mobile communication. Here we have the voice communication as well, but we start to have the broadband service, not to say broadband, but internet connection, where we call this as a data connection, where the user has limited capability of browsing the internet and sending data connection via the internet, right? Over the air internet connection. But the paradigm shift, we start on the data communication, we start to see on the 4th generation, which start in the 2010s. This is where the users has start to use the data communication a lot more than the mobile or the voice communication in the mobile network. So we have applications, right? This is era of the apps, where we have WhatsApp, we have the music streaming, right? The video streaming, social media platform that's like Facebook, Instagram. They start to evolve in the 4th generation. And across this 4th generation lifetime, we will see a lot more and more apps being used and being a major part of the population livelihood. Right? People start to do business online, and the usage of the mobile voice and data start to be equal. And at the end of the 4G era, we start to see a lot more data is being used rather than the voice communication. So when we start this decade, right, the 2020 decade, 5G has been started to be deployed in some countries, right? And we also have a test site in Malaysia. So in 5G, it's more about use cases, right? We have seen this famous triangle of the 5G use case. And the first one will be the enhanced mobile broadband, meaning the enhancement of the data communication or the connection from the previous technology in terms of speed, in terms of the coverage, right? So 3GPP or ITU have come up with the vision or requirement for 5G, to get like the 20 gigabit per second of throughput, as well as coverage across a certain area, right? The coverage quality. And this is the first use case of 5G, and when the first deployment of 5G will be focused on this first use case. The second use case will be the massive IoT or massive machine communication. In 5G, it is expected millions of sensors and IoT devices will be connected to internet. So this use case will have a different requirement in terms of the power, in terms of the because you're talking about devices that may be hidden in the garage, right? Like smart garbage bin and so on. So you need to have good power connection from the base station to the device, right? So this is the second use case of the 5G triangle use case, right? So the last and the third use case will be the ultra reliable low latency. So here you're talking about very fast and connection latency between the UE, the user equipment, and the base station, or from the UE to the network. And one of the example of this use case is we're talking about remote surgery, where the doctor is remotely located from the patient, and we are talking about using robots to do the surgery, right? Remote surgery. So the connection latency has to be very good. We're talking about 1 millisecond vision that is come up from the ITU. Right? So these are the evolution of the mobile communication from the first generation up to the 5th generation. So the main pillars of 5G, what's make 5G different from the previous technology, especially for 5G? For me, there are four aspects. And these aspects are very important when we want to measure the EMF, specifically for 5G. The first will be new spectrum. So in 4G, the mobile network use just a single range of spectrum from 600 megahertz up to 3 gigahertz. But in 5G, we start to have a segregation of frequency ranges. The first is, we call it sub 1 gigahertz. This is below 1 gig of frequency, and the usage of this is not for capacity, it's more towards the coverage. And at this frequency range, it is very good for the massive IoT, because we can go further in terms of the connection from the base station to the device. The second one, and this is mostly used for the enhanced mobile broadband or the generalized 5G usage, is the 3.5 gigahertz range or the sub 6 gigahertz range, right? So at this frequency range, mostly where the deployment is being made right now, right? So when we want to do the EMF measure, we have to consider the different frequency, especially at the C-band or this 3.5 gigahertz range. And the third range, we're talking about this millimeter wave, which is a very high frequency, right? From 26 to up to 40 gigahertz, right? So at this frequency, the focus of the performance is on the capacity, right? Because we have a very wide bandwidth available for capacity data transmission. However, the drawback at this frequency is coverage, right? So a lot of planning need to be made at this frequency range of deployment, and it has to be very specific on the use case and the target application. The next main pillar of 5G is the multi-connectivity. In the past, where we have the 5G base station. It's called as a 4G base station. We call it E0B, and we have a 4G radio access network. We call it 4G RAN. So you just have 4G RAN connect to 4G base station, and that's about it. But in 5G, right, we can have multi connection, right? Multi connection where you can have the 4G core, the E0B, still connected to a 5G radio access network, 5G antenna, right? So basically, the first connection will be made by the 4G network as a main node, and there is a handshake or the data start to be transmitted, then the network will shift from 4G to the 5G network. Right? So this is one example of the dual connectivity. There's a few options as specified by 3GPP. It can be vice versa, where you have 5G core connected to both 4G RAN and 5G RAN, right? Or in a standalone mode, right? You have 5G node B or G node B, 5G core connected to the 5G antenna. Right? So there's a few connection, and this is called the multi-connectivity aspect of 5G network. This is another factor that we need to consider when we are doing the EMF measurement. And the third one, and this is very important, is the massive MIMO or beamforming. Right? So in 5G, we start to have beamforming not just for the base station, but also from the UE. So you have going to have a targeted area that will have higher power of emission from the base station as compared to the rest of the area. Right? In 4G, you only have a single beam for each sector, so you have a uniform exposure. Whereas in 5G, you can have different level exposure at different area or a different point on the coverage area of the site. Right? So this is particularly important when we want to do EMF measurement, because we need to consider the worst case possible, means the highest emission at any point of the base station coverage. The last one on the main 5G pillars is the network flexibility. Right? This includes the different physical layer numerology, right? The network slicing, and also the virtualization of the network function. Right? But important here, I want to highlight is the in 4G, right? You have only what you call a constant size of the modulation symbol, right? Or the subcarrier spacing, right? Subcarrier spacing about 15 kilohertz. But in 5G, it can be varied from 15 kilohertz, 30 kilohertz, or 60 kilohertz, or even up to 120 kilohertz or 240 kilohertz. This is very important because when we talk about the EMF 5G emission methodology, we need to consider this, and there is a table for extrapolation that will consider the different subcarrier spacing size of the signal, right, coming from the base station. Right. So now we talk about the evolution of the mobile communication. Right. In the earlier generation of mobile communication, we have one sector here that has a maximum number of users that can be served by this sector. So when over time, right, then we have a lot more users that need to be served by the base station. So we start to do a segregation of the sector. So from one big sector here, so we start to have a base station. We have 3 sectors, right? And again, over time, we have more users, so we are dividing more of the sectors to cater for more users, to put more users to be served by the base station in the same area. Right? And across the development of the mobile communication, we also start to have the beamforming. Right? The 5G base station, or sorry, even in 4G base station, we start to have a beamforming that is targeted the data beam to the UE. But before 5G, the UE does not have the beam capability itself generally, right? Only from the base station, you have the so-called the beam targeting to the UE. Right? So if you look here, right, in 4G, you only have a single beam or unidirectional beam from the UE, right? So when the user is using the phone and the phone is not properly targeted to the base station, right? It may not be the optimum connection. You can have the beam directed from the 5G. It is smart enough even in 4G to the UE, but the UE was not smart enough to direct beam to the base station, right? But in 5G, it is expected that even the UE will have its own beam. It's a smart beam connection, right? So the base station will target the beam to the UE, and the UE will also have targeted beam, right? So for the uplink downlink connection here. So what it means here, right? You will have an area where you have a double and overlap emission from both the base station and the UE. So this is something to need to be considered, because the 5G UE is expected to have narrow beam track with tracking capability, and it can go to multiple direction to track for the base station location. So how does the 5G base station works in terms of this beamforming? So basically in 5G, right, the antenna is basically an array of a patch antenna, right? So you see in the circuit wise, there's a schematic wise, it has multiple small antenna here, right? So for example, in the millimeter wave, it can have up to 64 of this single element, right? So this element will have its own beam and a beam direction, right? So the base station can track the UE by manipulating the beam of the element from the 5G base station antenna, right? So this is a smart and active array antenna that's being used from the base station to give so-called a higher connection or better coverage from the base station to the UE, right? So meaning here there will be an area that has a higher concentration of emission and some area with less or even no coverage from the base station because there's no UE there. So in 5G, right, there are two types of beam that we need to consider, right? The first is called the SSB or the synchronization signal. This synchronization signal is always on signal. So it's always on and it will always moving. It's always tracking, right? It is at relatively, depending on the network setup, it is relatively lower in power as compared to the second beam, which is a data signal beam, right? So the 5G base station or the G0B will send an array of synchronization block beam. Once it connect to a UE, right, then the base station will start to send a data signal, which is a more focused beam and with higher power. Means that it's already have the connection from the UE to the base station. So this is developed to give better coverage so that you can go further with a focused power of transmission from the base station, as well as to efficiently manage the power consumption at the base station. Right. So this is how it works when the 5G base station connect to the UE. First, in the resource block symbol in 5G, right, you can have, for example, here 4 SSB or the synchronization beam being transmitted. And this is always on signal, right? So it's track the area to find for the UE, right? And then what happens that one it sweep and find the UE, right? It will send this information, the synchronization and also the system information block to the UE. And the UE will acknowledge and send a radio access preamble, right, to the UE to tell that which of these synchronization block beam 0, beam 1, beam 2, beam 3, that it is it prefer to connect to, right? For example, it prefer to connect to this one, the light blue beam, because this is the one that is the strongest beam that it is received, right? Then the base station will acknowledge and it will send the data beam, which is, you can see here, is narrower in terms of the angle and higher power. So this is where you start to have the connection data control, right? So this is particularly important because when we want to measure the EMF, right, we are using a passive device. We don't using an active device. Active device means the UE that you have a connection, SIM card connection, and you can have this a dedicated data beam. So when you do the 5G EMF measurement, you only measure on the measurement side itself, the in situ measurement. You only measuring the SSP beam, but there is an extrapolation factor to consider for the higher emission possible when there is a data or when there is maximum data transmission. Okay. So next, I will go to the second agenda, which is on the case studies on recent development of 5G EMF exposure policies, guideline, and standard at various countries. So just to recap, the electromagnetic wave, right? They are considered, you can categorize it in two sections in terms of health. One is the non-ionizing and one is ionizing. The ionizing frequency range is where it is dangerous and hazardous to the human, which is where the cell can be mutated when exposed to when the person is exposed to the rays, right? But there is the non-ionizing category where the range of the wave or the ray from the source is not dangerous, right? It's not going to mutate the cells, and the radio communication for the 2G, 3G, 4G, 5G signal are actually on the non-ionizing range. And just to take note here, the infrared and ultraviolet, so this will be the sunlight area. So the sunlight ray is actually more dangerous and hazardous as compared to the mobile communication frequency. But nonetheless, there is a standard that required for regulators and operators to meet in terms of the EMF exposure to prevent the heating up of the body tissue. Right? So there is a few reasons why we need to do a 5G EMF measurement. First is because we want to make sure that the public is confident that the technology does not harm their children, their parents, right, to the community. Apart from that, the reason why we need to do 5G is because we need to reboot the misinformation. Right? There's a lot of fake news that mention that 5G can cause death to animals or can cause the transmission of the coronavirus and so on. The reason why we need to do 5G EMF measurement with the proper method is to reboot this misinformation. Secondly, right, if there is a complaint from the public, it can delay in installing the base station, and this will cause it will be costly to the operators, right? And once we have this delay or the postponement of the technology due to EMF concern, then we are going to have economic cost for the society, and also to address if there is any concern on the environment, such as what is the effect of the 5G EMF towards the animal and the plants. Like for example, there is concern that the beekeepers will have concern that 5G radiation will cause disorientation for the bees to collect the honey and to go back to their hive, right? So those are the things that we need to address, and this can be done by doing the proper measurement of the 5G EMF, right? So in terms of the EMF standardization, it depends on few parameters, right? So basically, this is a study on the influence of the electromagnetic field, right, on human, right? And the parameter that is dependent on the first, the frequency. Remember, 5G we have different category of frequencies now, so it is very important to take that into consideration. The field strength or the power density of the power that is transmitted from the base station, exposition time, right? If you look at some of the standard by ECLIP, they mentioned, or like 1 minute, 6 minutes, 30 minutes. IEE mentioned 30 minutes. So there is some confusion there. But the question here is, what is the correct time we need to spend to measure the EMF and get a good result or acceptable result. And then the next one is important in terms of 5G EMF is the modulation. Right? This is where we start to talk about code selective measurement. We need to specifically measure for 5G signal. Right? So we are considering the beamforming, the subcarrier spacing. So we have to consider that. So this is the other parameters that we need to take into consideration when we do the 5G EMF measurement. Right? Of course, we're looking into international recommendation on how to determine the EMF exposure correctly. And also we have to consider that some countries have different limit. They are more stringent sometimes as compared to ICNIP, for example. So these are the aspects that we need to consider when we're talking about the 5G EMF measurement. So in terms of the health perspective, right, we have ICNIP that is recognized by the WHO. The limit that is recommended by ICNIP is recognized by WHO to be safe. So ICNIP has come up with a new version, May 2020, right, with the update on the recommendation of the limit line for the EMF exposure coming from the base station. Right? But ICNIP only specify the limit. So how do we actually do the measurement? Right? So in terms of how do we do the measurement, we have to look at other standards. One of them is from this IEC, right, International Standard, specifically for base station. There is a document called IEC 62232. The last published document is 2017, but there is a draft, 2020 draft, which is going to be released soon by IEC, 62232 2020. So in this document, in draft document, IEC, it mentioned the method, the recommendation method to determine the EMF exposure for 5G. Here NR, here new radio, here means 5G, right? So it generalized the requirement of 5G as specified by the 3GPP, and then it specified the method of measuring the 5G EMF, and you can see here there is an equation where you are measuring the emission level of the synchronization beam. Remember, we have synchronization beam and data beam, but when we do the measurement, because we are using a passive device, we can only measure the synchronization beam, right? But to cater for worst case scenario in terms of the data beam, there we have the extrapolation factor, right? So the synchronization beam times the extrapolation factor. So what is the extrapolation factor? Here I will discuss more when we go to the chapter 4, but it includes the different power of beam between the data beam and the synchronization beam. It also includes the bandwidth, sorry, the subcarrier spacing, right? The FPW is a subcarrier spacing, either it's 50 kilohertz, 30 kilohertz, or 60 kilohertz. So in IEC document, there is a table that shows that if the base station is transmitting or operating at 15 kilohertz at 100 megahertz bandwidth, then this is the factor that you need to put in here. Right? And the last one will be the FTDC, which is a technology duty cycle. So this is important because in 5G, the majority of the deployment will be in TDD, or time division duplex, where you have the same frequency range for both 5G, for both downlink and uplink. So the ratio here will be determined, will be put in here. For example, if you have 4:1, or sorry, let's say 3:1 ratio, means that you downlink 3 times and uplink 1 time in the time domain. I say downlink, 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 uplink, right? So it's 3:1. So FTDC will be 0.75. Right? If it is 4:1, right, means that 4 times downlink and 1 time uplink, then FTDC will be 0.8. It depends on the network setup of the operator. So let's look at the first EMF case study, right, made in Switzerland. So the initial study by the authority in Switzerland, METAS, had been rejected by the public. So the regulator have to come up with a new and more comprehensive method to 5G, and this has been presented to the public inquiry, public engagement, and it's been accepted. So what I want to highlight here is that in Switzerland, for 5G specifically, they're using the code selecting methods to do the 5G EMF determination, and that is actually consistent with what been explained by the IC draft document. So you can see in this document, in this Switzerland technical report document, it does mention here, right? You have the synchronization beam and you have the data beam, right? So there will be an extrapolation factor that you need to put in to consider the maximum exposure when there is maximum traffic. And here is an extrapolation factor, which slightly a bit different from IEC, but fundamentally it's about the same. So this is how Switzerland do it, and then this is only in their country. But as a general code selecting method, the IC 62232 draft 2020 can be used as well. So in terms, there's another country, UK. The UK also come up with the case study, right? But this same case study, the same method actually being rejected in the Switzerland. Right? So how they do it is that they're doing a very simple measurement, right? So they choose about 16 5G enabled mobile phone base station, right? And they measure for all the technology, 2G, 3G, 4G. So what it does is that it's not really practical in my opinion, because what they do is that the base station will transmit first 2G, and then second 3G, and then second 4G, and then the third one with 4G, and then the fourth one will be 5G. So it transmits in sequence. This is not really true in real life, where we have all this technology transmitted together, right? So the reason is because they're not doing the code selecting management, so they try to use a normal broadband management and try to get a single data for each frequency range, right? So if you look at the conclusion for that study, right? It says that EMF exposure level from 5G enabled base station remain at a small fraction of the reference level, okay, right? From the ICNIP. The highest level recorded being approximately 1.5% of the power density reference level. Okay, what it means here is that you have an ICNIP level, but the exposure limit is just 1.5. However, please take note that there is no data transmission and there is no extrapolation is being taken into consideration on this report. In all locations, the largest contribution measured level come from the previous generation of mobile technology, 2G, 3G, 4G. This is what they claim, and they mentioned that for 5G, it is actually very low as compared to the previous technology. But if you look into the, remember you have the beam and data, the data beam and the SSB beam in 5G, right? By right, in theoretically, right, the 5G emission should be higher than 4G when there is maximum traffic. And the reason is that because they are doing a very simple measurement where it just have a normal isotropic probe connected to an EMF reader, right? It doesn't discriminate between the technology, so, and they are not considering the beamforming aspect as well as the extrapolation. So this is a case study from UK as compared to the one from Switzerland, right? You can see in terms of the public awareness, the countries like Switzerland have a higher concern on their health as compared to some other countries, right? For example, the UK. But anyway, just to go back to this ICNIP level, right? So ICNIP 2020 has come up with a new reference table in terms of the exposure limit. So for the occupational worker, the power density is about 50 watt per meter squared, right? At this higher than 2 gig signal. This is where majority of 5G signal will be in, which is at 3.5 gigahertz and also at 28 gigahertz. So the limit for the workers will be 50, and the limit for the public will be 10 watt per meter squared. The reason why we have different limit for workers and public is because we assume the workers are adult that have been trained, so they know how to protect themselves, and they need to go nearer to the 5G base station. They need to be slightly exposed by the 5G by the base station, because they need to set up the equipment. But and they may have access. They may need to go to some area that cannot be accessed by the public. Whereas the public, the limit will be 10 watt per meter squared because it includes all children, infant, old, the senior citizen, right? Which, and also they are not trained to protect themselves from the emission. So we have a stringent limit here, a lower limit, 10 watt per meter squared. So anything above this is fail when it comes to the public exposure at the coverage area. Okay, so that's the update from ICNIP 2020 in terms of the exposure limit. Right? So this is again in ICNIP 2020, they got or the historical limit line that's come up from ICNIP. You have initially the 1998 limit and the 2020 limit. So you can see that the 2020 exposure density is at 10 watt per meter squared, and the electrical field is about 60 volt per meter. And this is the limit here, means that you have to measure it more than 6 minutes. This is a disposition time, right, for 6 minutes. You have to at least measure for 6 minutes, and to ensure the result across that 6 minutes to be lower than the power density limit or the electrical field limit stated by ICNIP. Okay. Next, we go to the third agenda, which is the differences of the 5G EMF radiation measurement as compared to the legacy technology. So basically, in the legacy technology, we are doing the frequency selective measurement, or either the broadband, or in some cases the broadband measurement, right? So what it does here is that it's only measured on the overall signal, which is the received power, right? Whereas the co-selective measure on the known signal, known reference signal, and also the received signal, received power of the base station, which is the effective power that is being exposed to that coverage area, right? And to do the measurement, we need a device, an instrument that can measure either the RSSI or the RSSP connected with the probe or the antenna with a known factor, right? Because we need to include this factor for the calculation, or at least to be compensated by the instrument if the instrument is small enough, right? So what they do is to measure the known at the signal level at this antenna and convert it into field strength. So in terms of the legacy method which can still be used in the 5G EMF, the first is the pivoting method. So this is when you do a 6 minute measurement, right? You do a pivoting where you move the antenna across a circuit. You do we call it stirring. You stir the antenna until you get the maximum exposure, right? So that's why you need a 6 minute measurement disposition time, because you need to stir the antenna until you get the maximum field value, right? So this is can be done by using a handheld measurement equipment on the site, and also you need to have the software that is able to show both the actual and maximum value, right? So when you move the area, when you move the antenna, right, it will detect first the current value, and it will lock down the maximum value. So you will see two values here, right? And when it detect a higher value, then the max value will also be updated, right? This method will suitable only for one service at a time. Means if you want to measure 5G, you do 5G measurement only. If you want to do 4G, you do a 4G measurement only, right? So it's not a generalized EMF measurement for all technology. Another method we're talking that has been developed by some standard, for example, EN 50400 or EN 50492, is that you do a over distance measurement. You move the antenna like every 40 cm offset, or every 1 meter offset, or half meter offset, right, separation, and you measure at three height, 110 cm, 150 cm, and 170 cm. So this to simulate the head area of children, female adult and male adult. So this to basically it's trying to measure the maximum total exposure ratio at the 3 important measurement point or measurement height of the human body. Right? And of course, we can have the in one of the selected site that we can do a long-term analysis, right? Remember when we talk about Eclipse, they mention about 1 minute measurement, 6-minute measurement, 30-minute measurement. So how do we verify that this, let's say 6-minute measurement is acceptable? So we select a site, just one site, then we can do a 24 hours measurement, right? Then the measurement data will then be compared to the 6-minute measurement to at least give us the confidence that the 6-minute measurement is consistent with a long-term measurement value, right? So then from here, we can say that 6-minute measurement is sufficient. Right? And some regulators or in some countries, right, what they do is they have this one site that they connect 24 hours for measurement, and they display the result, they stream the result in their website so that the public can have access and have a look at the real-time data of the EMF exposure. So in terms of the legacy measurement, these are the various measurement methods. First, you can have the personal monitor, where the employee that work in the near the base station, the operators, the network vendors, they put in a personal monitor here for fast scan, and this is only used for personal protection. So it can detect what is the exposure limit in terms of the voltmeter of the person of the worker, or when going near or close to the base station. Another one is a broadband meter, right? So it is a device that does not discriminate the technology or the source of the EMF exposure. It just measures the total EMF measurement at this area, right? So it's a very simple measurement. It can only measure for root mean square value only, right? This is for a very quick and it's actually good enough for 2G GSM last time, right? So when do this measurement, when there is only 2G that is transmitting in the area, right? So we can safely assume that whatever measurement that we read here is coming from that 2G base station. But in the modern times where we have 2G, 3G, 4G, 5G base station, so what you read here will not tell you from which base station or which technology it is reading. Right? So that is the pros and cons of this broadband meter. The other method will be the frequency selecting method. So you can, this is you start to select a base station, right, or an element of the source of the signal, right? So this basically you have a spectral analyzer connected to isotropy antenna, and now you can select the frequency range. Right? For example, you want to measure at 2.7 band 7 frequency range, right, for LTE, then you can use this method. But going forward, for when you talk about, even in 4G, right, we start in 3G, 4G, we start to talk about code selective method. So code selective method has the highest flexibility, means that you can measure specifically for a single site, single technology, single sector, single SSB beam, right? So you can have a very the high granularity of data, right, of selection of the parameters, right, as compared to the previous method, right? So it can able to decode the signal and tell you, okay, you are measuring this EMF measurement from this sector A and this sector and this SSB index 1, for example, right? So then you can use this data value to put in the equation as specified by IEC, as I mentioned before, right? And add or multiply it with the extrapolation factor, right? So this is the advantage of using the co-selective method, because now we can consider for beamforming, you can consider for the different frequency range of the signal, you can consider for the different sub-carrier spacing, right? Because of you are doing a code selective measurement. So these are the probe and equipment to be used when we want to do an EMF determination. So let's talk about the extrapolation factor, right? And why it is more complicated in 5G. In 4G, you only have one beam for the sector, right? So it is easy to extrapolate, right? I don't want to go through the details of the equation, but basically you have a single subcarrier spacing of 15 kilohertz. You have a single beam, right? So wherever you do the measurement, you would roughly get about the same value after you put in the extrapolation factor. And you can see the equation for the extrapolation factor is straightforward. Right? It's very straightforward. Whereas in 5G, remember we have the beamforming, right? The beamforming, you have the TDD, FDD, right? The TDD factor, right? You have to consider, and you have a different subcarrier spacing. So all these parameters or aspect of 5G that prevent that for it to be properly determined if you are using the older method, or for example the frequency setting method, for example, right? But you can no longer use a simple calculation like this to measure the extrapolation factor, right? So for the 5G extrapolation factor, you need to consider two steps. The first step is, sorry, when the 5G determination method, right, is consists of two steps. The first step is to get the extrapolation factor. And to get the extrapolation factor, there are three components. First is the, remember we have the different, the SSB, right? We need to have the SSB, right? What is the difference in terms of power when compared from the SSB to the overall bandwidth of the signal, right? Here is where you need to refer to the subcarrier spacing of the base station, right? Second is the beam gain offset between the SSB and the data beam. Remember, we have the SSB beam here that is on, and also the data beam when there is UE connected to the base station. So we have to consider for the worst case scenario when we have the data beam, but when you do the measurement, you only measure the SSB beam. So you need to have an extrapolation factor that caters for the data beam. And the third component will be the uplink and downlink factor in the TDD. Right? As mentioned, we have, let's say it's half the time downlink, half the time uplink. So you need to multiply this extrapolation factor with 0.5. Or is 3 to 1, that is 0.75, or 4 to 1 is 0.8. Right? So this is the extrapolation factor determination of the 5G EMF. It is step 1. And then step 2 is to do the measurement of the SSB index. So what you need to do is you are measuring, remember in terms of the equipment used for the EMF, right? All of the equipment are passive. So you cannot measure the data, you can only measure the SSB. So the second step is to do the actual measurement of the SSB beam. Then you have to add that in all the beam from that sector, right? From that particular PCI. So that you can do a quadratic sum. You can say this is a summation of all the beam exposure value, and you square that summation and you do a square root. So this is called a quadratic sum of the all the SSB beam exposure value. So you have a first step, the exposure factor, and the second step is to do the actual measurement. Now let's go to the final agenda, which is on the case study of 5G EMF from some actual site in Malaysia, right? Okay, so the first site, we did a measurement in UTM KL, right, for the 5G EMF measurement. So we have the 5G base station here. So this is the LTE or 4G exposure limit that we measure, and this is a 5G. You can see the 5G actually higher when you consider the beam that is more focused in 5G as compared to 4G, right? So, and the measurement has been done here, and now we want to do the full EMF calculation. So this is the location of the measurement, right? And we detect two SSB, right? SSB 300 and SSB 001. The first SSB, this is a maximum value. The second SSB, this is the second maximum value for the exposure limit. We know the downlink and uplink ratio is 4:1, right? The signal bandwidth is 100 megahertz and the subcarrier spacing is 30 kilohertz based on the measurement, right? Using the tool, right? So this is a value from the SSB 27.8 millivolt here, and this one is 37.5 millivolt per meter. Right? So now we go to the equation from IEC 62. If IEC 6232 method is used, then we start to put the value, right? Remember this FBW. How do I get this FBW? This is the total number of subcarriers within the carrier bandwidth, right? So we know it is 100 megahertz bandwidth and 30 kilohertz subcarrier spacing. So based on the table in IEC, 30 kilohertz, 100 megahertz bandwidth, the factor is 3.276. That will be here, FBW. Okay. The TG ratio is 4:1, so it's 0.8. The FPR here, which is the power actual maximum, the different power between data beam and the SSB beam at that side is actually 1. It means it's the same because it's a test site. Right, so it's 1, and we have 3.276 here. So we start to put all the value, right? We also do a quadratic sum on the total measurement of the SSB. That will be here, right? There is a quadratic sum here, right? So then we get this value. So this total SSB quadratic sum value we put here as 0.0467 plus square root of 3.276, where we get from this table. 1 is the FPR, which is the different data beam and the SSB beam. 0.8 is the duty cycle of the TDD. So you do the calculation, so you get the total exposure limit at this particular site during that time when we have the 5G base station, 3.5 gigahertz. It's about 1.67 volt per meter. This is the value. Right. So this is the first case study that we have done. The second case study we did in Langkawi, but this is not made by Professor Adwati and her team in UPM. So it is in Langkawi Island in Puah. I believe this is a TM site. So this is a more proper base station as compared to the one in UTM, because this is it's actually behaving as a real base station where you can say there is a multiple beam for the sectors, right? So this is the area that we do the measurement, right? So the study of this from the UPM is to find what is the best location when you want to do the 5G EMF measurement, and also what is the best disposition time. So they're using the equipment and they are doing a code selective measurement. So this is a first set of location that they do the measurement, and which is nearer. And second set, which is further away. Why they are doing measurement? Because they want to find the best location in terms of the exposure. So they found out that in terms of the exposure limit for 3 different deposition time for these 2 set of location, you can see that at the site where it's nearer, right, it is about 9 volt per meter of exposure, right? And you can see that from 6 minutes and 30 minutes, there's not much difference. Whereas on the second side, right, it's actually higher EMF value, right? You can see it's about 11.5 volt per meter. Right? And of course, from 6 minutes to 30 minutes, there's not so much, there's no significant difference. Right? So you can see that we can actually do a measurement of 6 minutes as recommended by IGNIT, because there will be not much difference between 6 minutes and 30 minutes. Right? But in terms of the location, you see, when you are, it doesn't mean that when you are nearer to the base station, the exposure limits, the exposure value is higher. You can, the highest exposure value can be on a further location. This is where you have they want to find what is the best angle where you want to do the 5G EMF to get the highest maximum value of EMF exposure. So this is a table of the result from Langkawi, right? In terms of the 1 minute, 6 minute, and 30 minute for the first location. This is the value of after the extrapolation limit, and this is for the second location for 1 minute, 6 minute, and 30 minute position time. Okay, so I've come to the end of my presentation. So to summarize the presentation, right? The first is that with commercial 5G network being rolled out, the EMF measurement is considered a prerequisite, or at least it has to be done on selected site to prove that the radiation is below a certain limit as recommended by the standards. Right? Especially here is ICNIP. Right? When it comes to the higher generation of mobile communication, for example 5G, we need to have extrapolations. We need to have equipment that is able to measure the RSRP, right, of each component of the signal to able to do this code selective measurement. Then we can determine a specific base station exposure value, rather than you are using a normal broadband measurement or the frequency selective measurement, right? So you have a higher granularity and higher selectivity with the code selective measurement. And lastly, to summarize this, is that the international standards such as IEC 6232 can be used to calculate the effective EMF exposure coming from the base station, especially the higher generation of base station, for example 4G, 5G, where we need to take into consideration the RF measurement and also the technology extrapolation factor, which is the beamforming factor, the different frequency range factor, and also the sub-carrier spacing factor. Right, so I've come to the end of presentation. I have 3 minutes for question and answers.
Thank you, Encik Anwar, for the very informative presentation. I find the case studies section was very, very good and very much interesting. So we have 3 more minutes for Encik Anwar's time. So anyone, any questions, just throw it out. You can either talk through the audio, or you can even write up through chat for any questions.
Hello, Encik Anwar.
Yes, Mr. Rizal.
Rizal from Penang. Can I assume that EMF level for 4G, 5G is better than 4G?
No. That's we have to determine it based on the technology. So when you say better means lower, right? Which I believe is not based on what I measured, right? Especially in KL here, and also from theory, right? You can see that 4G in the same area, I am measuring at this level 0.007 millivolt per meter, but for 5G it is higher. Now this is because, remember, in 4G you have just a single beam, so the power is distributed evenly, whereas in 5G you start to have a focus beam, right, from the base station. So you can actually have, by right, in theory, you should experience higher exposure on a certain location of the base station. Some area you may have very less or not even, there's no exposure at all, but some area is way higher. That is different between 5G and 4G. And we have to take that into consideration.
Okay, thank you.
Next questions, please.
Hello, Encik Anwar.
Yes.
Fadil from Penang State Office.
Yes, Fadil.
I would like to ask about testing in Langkawi.
Yes.
Which frequency you use for this test?
3.5.
Frequency 3.5 gigahertz lah.
Yes, it's an outdoor C-band, which is allowed in the area in Kuala.
Only one band lah.
Yes, only at the 3.5 gigahertz for this type.
The result average is about 9 to 10 volt per meter, right?
Yes. After the extrapolation, yes.
It's quite high.
This is a final result, right? Please take note that I did not went to the site. It's by Professor Adwati from the team. I provide consultancy and also the equipment. But this is the report from her test. And their method of measurement is using the IEC 6232. Their focus of study is they want to find where is the best value, the optimum value to measure for the 5G EMF from the base station, based on this for the angle on the height of the base station and so on, and also what is the best deposition time. So they're taking the 3.5 gig 5G signal in Kuah, I believe is TM, right? I may be wrong here. So that is the focus of the study. Any more questions?
Any more questions? I know that we have already reached out the extra 1 minute from the 3:30 mark, but it's okay. If any one of you have any questions, you are free to ask.
Cik Anwar,
Yeah.
I just would like to make a suggestion. Perhaps if you have time to spend in Penang to also do EMF tests in Penang, because we have the 5G trial as well.
I would love to, right? Maybe after
At the
MC. Maybe you have my contact, right? You have my email address.
I will get it from the secretary.
Okay, I put that in comment. Maybe after the MCO.
It's for free, right?
Yes. Yeah, all this while is free. It's more on the study that we make. That we want to find what's the right method to do the measurement. So please email me. But of course we can't go now. Maybe after coast is clear from from the virus perspective.
Yeah, because there's one nice place that you can actually do conduct the test. The top hill of Penang, Bukit Bendera. There's one 5GDP there.
That's
very
good.
very cold place. Owned by DG. So maybe
I see.
you can conduct the test there.
Yeah. Actually, apart from the Langkawi, I also done some measurement in my app just before the MCO announced. I think about first week of January, right? But I haven't summarized or compiled the data yet. So I would like to get more data for this. So if we can go to Penang and do the measurement, I would be very happy to do it.
Okay, good. Thank you.
Study purposes, yeah. Thank you. Thank you for the invitation.
For everyone's information, Encik Anwar has already posted his email address in the chat in case any one of you wanted to reach him. So any more questions, anyone? So can I take it that there's no more questions? Yeah, I'll take that as no more questions. So Encik Anwar, thank you very, very much from the bottom of KMRC's heart. Thank you very, very much for your time. And to
Thank
all
you
our
for
wonderful
inviting me.
participants.
Thank you. Yes,
Oh,
thank you.
okay.
Thank you
No
to the
problem.
participant for joining the session as
Yeah.
well.
Thank you to the participants as well. So you have Encik Anwar's email address if you want to reach to him. And in case that you wanted to reach out to Encik Anwar in between, from KMRC side and so on, you are feel free to do it as well. So Encik Anwar, we also hope that we will stay in touch for future collaboration or future presentation sessions.
Sure.
So again, thank you everyone. With this, I'll end up the session. Thank you
Right.
again.
Thank you.
Bye-bye.
Thank you.
Terima kasih Encik Anwar. Terima
Terima
kasih.
kasih.
Terima kasih banyak-banyak Encik Anwar.
Terima kasih.
Jumpa kat Penang.